Okay, guys, so in this example, this is problem number 7 from page 174 of G and Coley 5th edition. And it says, what is the minimum work needed to push a 1,000 kilogram car 300 meters up a 17.5 degree incline? In part A, it says ignore friction. And then in part B, assume the effective coefficient of friction is 0.25. Okay, so the first thing we want to do, we have the car here being pushed up the incline 300 meters, 17.5 degree incline. First thing we're going to do is draw forces acting on this thing. So what we have is the force of gravity, which is in this direction. We have the normal force, which is in this direction, and we have the applied force. We're going to leave the force of friction out for now, since it says to ignore friction in part A. Okay, so hopefully by now you've looked at enough work problems to know that the work done by the normal force here is going to end up being 0. And the reason I say that is because whatever that normal force is, we take that, we multiply it by the displacement of 300 meters, and then the cosine of the angle between them. But the angle between that normal force and the displacement is 90 degrees exactly. And the cosine of 90 is 0. So even though this is a force, it's not going to do any work. So the work done by the normal force is 0 joules. Next, let's find the work done by gravity. So the work done by gravity is going to be the gravitational force, which is this, 1,000 times 9.8 is 9,800 newtons. So that's the force. It's a 9 there. Times the displacement, which is 300 meters, times the cosine of the angle between that force and that displacement. So we've got to be careful here. The direction of the force is straight down. The direction of the displacement is up the incline. The angle between that and that is going to be 90 plus 17.5. We get 107.5. So I'm going to put that in here. Okay, and I'm going to grab my calculator. Make sure that I'm in degree mode. 9,800 times 300 times the cosine of 107.5. We get a really big negative number, negative 884,075. Now you might be wondering, why is that number so big? Well, you're trying to push a 2,200 pound car, 1,000 kilograms, 2,200 pound car, almost a quarter of a mile up a pretty steep slope. 17.5 degrees is quite steep for a road. All right, so that's a lot of work. All right, now, here's the thing. There are 3 forces in this picture: weight, applied force, normal force. We already took care of the normal force. We already took care of gravity. The problem said, what is the minimum work required? Well, if it's the minimum work required, that means no acceleration. And if you remember, that means the total amount of work has to add to 0. Anytime we see that no acceleration or minimum work required phrase, we know all the works together add up to 0. So whatever the work done by the applied force is, when we add up all 3, we have to get a total work of 0 joules. So that means this must be positive 884,075 joules. Okay, so the work done by the applied force is positive 884,000 or so joules. So that's part A. Now, in part B, there's friction. So if we add the frictional force in, if you think about the task, now the person who's pushing the car is going to have to push harder. This answer is not going to be true for part B, because now you're working against gravity and against friction. Okay. If we add up all the works, we still have to get 0, but the force of friction is going to do some work also that we have to watch out for. Okay, so in part B, the normal force still does no work. And the work done by gravity doesn't change. It's still negative 884,075 joules. But here's the problem. I don't know the work done by friction. And I don't know the work done by the applied force either. When I add them all together, I still get 0 though, because we're still talking about constant speed. So here's what I'm going to do. I'm going to find this force of friction and use that to find the work done by friction. Now you got to think back to the fun equation that we learned in Newton's laws. Force of friction equals mu times n. And another thing that you need to remember that we haven't seen in a little while, when an object's on a slope like this, the normal force ends up being equal to the component of gravity that's opposite it. So like this way, this component of the weight. That component of the weight has to equal the normal force. And if you remember, that's mg cosine of that angle. Okay? So to do this, I'm going to do 0.25 because that was the coefficient they gave us. And then the normal force is mg, which is 9,800 cosine 17.5. So let's do that. I think it comes in around 2,300, but I'm going to do it anyway. 25 times 9,800 times cosine 17.5. Yeah, 2337. Now be careful here because that is not the work. That's the force of friction. I still haven't calculated the work. But now I can do it. So I'm going to go 2337 newtons times the displacement, which is 300 meters, and the cosine of the angle between the force of friction and the displacement. The angle between those two, they're opposites. So it's cosine of 180 degrees. So I'm going to plug that in the calculator. Whoops, 2337 times 300. I get negative 701,000 joules. Okay, now think about it, guys. This plus this plus this plus whatever the work applied is has to add to 0. So I can figure out what this is. It's going to be enough work to cancel out that and that. All right, so that plus that. I get about 1 million. $585,175 joules. Now, obviously, we can round these things to sig figs. All right, so in the problem, I think they gave us 3 sig figs overall. Let me take a look in the book. Well, really two sig figs for most of it. It's not actually consistent in this problem in the textbook. All right, so you could round that to sig figs to finish it off. But this is the work done by the applied force. You'll notice it's a lot bigger than it was before when there was no friction because you're working against gravity and against friction in part B. So that's basically it.